Hello. Well, so far we have discussed various aspects of signal processing, and you would have realized that the frequency content in a signal is very important to relate to the characteristic faults in a mechanical system. Well, in this lecture we are going to find out what are the methods to find out the frequency content in a signal other than the conventional FFT, and one being actually this signal heterodyning, which is useful for a technique which is useful for finding out frequencies in very high frequency signal, where actually we are not able to sample the signal at that higher frequency. Okay, so, we will see how signal heterodyning helps, because if you realize, if you want to numerically do FFT, I need to have an array of number x. Okay. And this array or this signal has to be sampled at a particular sampling frequency f s, where f s should be equal to twice f max as per the Shannon sampling theorem. But question is, when we have a signal, say for example, 10 gigahertz, for example, a very high frequency signal, which is not true in mechanical systems. We do not have such signals in mechanical systems. Okay. But perhaps some electromagnetic waves like radio waves, TV signals, etc., very high frequency signals. So, question is, if my signal is at such high a frequency, I need to have a sampling frequency higher than that. So, this is the limitation of the traditional hardware. Okay. The limitation of hardware in finding out such high sampling frequencies. So, it is not possible to get cards or data acquisition systems with a high sampling frequency. They are not available because the sampling times intervals are so small. So, there is another method which is signal heterodyning, which we will discover or try to understand in this lecture. But before that, let me try to kind of quickly tell you what are the other methods available to determine the frequency of a signal. You would have seen, if I compare a known signal, say for example, x is equal to a sin omega t and y is equal to a sin 2 omega t. Okay, and if I plot x versus y, okay, we will see that there will be lobes and so on. So, if one signal is known, the other signal can be found out and so on. So, okay. This kind of orbit plots we have seen. Okay. If x is equal to y, I will get a straight line like this. If x and y are 90-degree phase difference, I will get a plot like this. Okay. So, this kind of orbit plots we have seen are helpful in finding out the displacements or amplitudes in a shaft, so which is rotating, supported on bearings. And if I look at this end view here, if I measure an x here with a transducer, y with a transducer, I can see if x and y are same or different by just plotting the orbit plots. So, physically for turbine, shaft, position, monitoring such plots are used, or bit plots, or they are also in the known as Lissajous figures. Okay. Well, another very easy way of finding out the frequency content of a signal, if it is a very slowly moving phenomenon, for example, a pendulum which is oscillating. Just measuring the time period of oscillations, how many swings it passes by in a given time, I can find out frequency is nothing but 1 by t. Okay. Many times in many slowly changing events, just by measuring the change in the signal, maybe ticks, okay, this is in time, some voltage. So, inverse of this time period, in fact, in the industry you will see that many times we need to monitor the rotational speed of shafts. How do you do that? So, example, a shaft is rotating. Essentially, a shaft has a key. A shaft is rotating. So, if I put a probe here, a reluctance probe, which senses the gap between the voltage produced is proportional to this gap here. So, every rotation of the shaft, I am going to get a pulse. Okay. So, this again the inverse of the time taken, or just by having an f is nothing but 1 by t, just by having a frequency counter. I can get the rotational speed of the shafts. In fact, simple device is used in many industries where online we can on the run measure the rotational speed. Okay, but then this gives you an average rotational speed. Later on we have seen how through this optical encoders we had to find out the instantaneous angular speed using optical encoders. The difference between an optical encoder and such probes is the fact that in the optical encoder the sensitivity is so high that within a rotation if there is a small change in the speed, I was able to sense it. But in such reluctance type pickup, okay, because of the change in the gap, the magnetic flux changes. Thus, we will have a voltage corresponding to this change, okay, voltage, induced voltage, and by sensing this voltage, I am able to get these peaks, and inverse of these peaks is nothing but the time period, and that is what we have got here as the rotational speed. So, inverse of the time period is a method to measure the rotational speed when phenomena are very slowly changing. You can just have a stopwatch and measure the events, how frequently they are changing and so on. Of course, the next technique is FFT. Okay. By now, we have you all must be knowing what this fast Fourier transform is. I will come to this filtering and heterodyning a little later, but let me tell you two most possible errors in FFT, because whatever be it, my purpose is to accurately estimate the frequency contained in the signal and the amplitude at that corresponding frequencies. Okay. Now, to do that, if I do some error in my frequency estimation, I will have a problem. The first one is what is known as the picket fence effect. This happens because of inadequate frequency resolution. Let me show you by an example. So, this is my time window. I have some signal. Okay. So, I have taken n points, well, or t is equal to n times delta t, n number of points, and the time interval between any such point is delta t, where f s is nothing but 1 by delta t. If I do an FFT, I will look at the magnitude of the frequency spectrum. NEF is some voltage in time domain. This is voltage absolute value. I may get some signal like this, where the spacing between two successive point is delta f, where the frequency resolution delta f is nothing but 1 by capital T. Now, question is, in a practical signal, suppose my signal has a frequency f1 is 23 hertz and f2 as 23.01 hertz. Okay. So, in such a case, my delta f has to be, delta f should be at least less than 0.01 hertz, right. But you see, delta f is nothing but 1 by n times delta t. If my sampling frequency is fixed f s, I can only increase n. So, that means to have fine frequency resolution, your n should be large as possible. There are, of course, there are limitations why n cannot be large because of the memory requirement, because every data point requires a storage space or a memory space. So, I cannot make n very large because that will be limitation of my storage space. So, this delta f, if it has to be fine, I need to make n larger and thus have adequate frequency resolution, so that I can represent a signal at its peak. Otherwise, I may miss. If the peak is somewhere here, I will miss it. I am sampling here, here. I may have missed this peak and wrongly represented it as this. But right amplitude was here because I did not have, this was not available to me. Delta f star is something much less than delta f. Okay. So, I am missing this peak, and that is what is known as this picket fence effect. Okay. So, to only way I can do for a fixed f s is increase n, and we will see in the subsequent class an example how through improving the n I can have delta f to very, very high. Yeah. Now, another possible error in FFT is what is known as a leakage error. See, for example, when we assumed or did FFT on a window of block, we took a window of n data points. Okay. If my signal is like this, the next signal would assume So, if I bring this signals closer, I will have maybe this kind of a gap. So, this is what is known as a leakage. To reduce leakage, what we do, we multiply the signal x with a windowing function, so that windowing function, so that the signal x which we go for FFT is actually dot product with the window function times the x original. Okay. X original is my sampled signal. Okay. So, so that I multiply x I to this window function. So, it becomes 0 at the end, and thus I have what is known as a continuous signal. So, this continuity is maintained and so on, and thus reduce leakage. There are many window functions available. Okay. So, that like the Hanning window, flat top, uniform or rectangular window, or the exponential window. Okay. So, usually for periodic signal, for good frequency estimation, such signal is used. This is for a good amplitude estimation, and uniform or rectangular window is actually a no window when the signal itself has no continuity, like a nice sine wave. Okay. There is no need to have, because if they will end at 0 and start at 0, so nothing is going to go wrong. Okay. In such case, you need not apply any window. An exponential is used for forcing functions, or where response is dying out with time. For example, so you can use an exponential window. Usually for modal testing, we will discuss this later on. Okay. So, to reduce errors in FFT, one is the picket fence effect. We need to have adequate frequency resolution. That can be done by increasing the number of data points we sample, and to reduce leakage errors, or to have a right estimation of the amplitude or the frequency of the signal, we need to window the signals. Now, I will come to one example wherein we will see when two frequencies are very, very close by, you can see that the phenomena where the amplitude actually increases and decreases, and this is what is known as beating. Now, even if these frequencies are very, very high, okay, then what happens? If the difference is very small, I will have this amplitude beating. Okay, amplitude is increasing and decreasing. But once the signal frequencies match, what is going to happen? I will have no longer increasing or decreasing of the signal, but a same signal. Okay. So, this is taken care of in signal heterodyning. For example, if I have a signal f naught, okay, and another signal f naught plus delta f, a small change in frequency, I will get a signal like this, cosine delta f t, okay, and sine f naught plus f 1 by 2. Now, if this delta f becomes 0, I will just have a plain simple harmonic signal. Okay. This is taken care in an method to find out an unknown signal. So, for example, I have a very, very high frequency unknown signal. Here I will have an oscillator, okay, and then I will sum it up. Okay, and look at the amplitude of the signal. Okay. So, this is my original signal f naught. I will create a signal here, okay, where f 1 is nothing but f naught plus delta f. So, I will be changing the signal frequencies here in this oscillator and generate this signal. So, whenever f 1 becomes equal to f naught, what happens? Delta f becomes 0, and then I will have a single. So, I would be normally having a beating phenomena, and but then once heterodyning has, then I will. So, such heterodyne analyzers are used to find out frequencies of large frequency signal or high frequency signal. Because as I was telling right in the beginning, when Fs is hardware with high Fs is not possible. One can do such heterodyning analyzers. Okay. Exact example I will tell you. Even we are going to study later on about laser vibrometer. Okay, where laser vibrometer works with the principle of Doppler effect. And laser frequencies are very, very high frequencies. So, such now okay, I can find out the velocity of the source, okay, depending on the frequency, okay, of the incident wave and the reflected wave, and these two values are very, very high. Okay. So, conventional FFT will not work. So, I can use a signal heterodyning, an optical heterodyner, to find out. If one is known, I can find out the other. So, that is known as the Doppler shift frequency. Once I know the Doppler shift frequency, I can find out the velocity of whatever is your source or target which is vibrating. Okay. And this principle is used in estimation of TV signals. On such analyzers are actually known as spectrum analyzers. For radio waves. Our conventional FFT analyzers may be today the maximum bandwidth we can have with such analyzers is 100 kilohertz, though mechanical systems we are happy with signals less than 20 kilohertz. Okay, that is the conventional FFT analyzers. And then we will see in the next class how such FFT analyzers can be used to demonstrate to you different signals. Of course, another technique of finding out frequency content of signal is through filtering. I will name it as analog filter. So, with a combination of RC circuits, okay, I can get some output depending on R and C. I can design filters and I can have series of such filters, and then for any signal I can have a filter which will have certain bandwidth, okay, and then this is the F lower and F upper. I will have a center frequency, and this is 0 dB. Okay. So, they sometimes say this as minus 3 dB. So, any signal which goes into a filter, okay, will come out depending on what kind of frequency were contained in such bandwidth. So, we will discuss about filtering later on in a separate class on the low pass filters, band pass filters, high pass filters, notch filters, etc. And then we will see how such signals can be analyzed through filtering, through analog filtering. So, to summarize, today we have discussed the different techniques of finding out the frequency content in a signal. The first being the orbit plot or the Lesser's figures. Then of course, a simple way of estimating the time period and inverse of the time period gives us the frequency. We have seen the errors which could happen in FFT, like in picket fence or the windowing, and how signal heterodyning can be used to find out the frequency content of signals which are very, very high frequency, where the conventional FFT analyzers will not work, and such analyzers which work on the principle of heterodyning are known as the spectrum analyzers, which are used for analyzing signals, high frequency signals like the TV signals and radio signals. And of course, we had and just mentioned that analog filters can also be used, or a series of such filters could be used to find out the frequency content of a signal. Thank you.